Welcome back. We are in topic 2, aqueous reactions, lesson 2, where we're going to look at different ways to calculate solution concentration and other variations of those types of problems. So today you'll be able to calculate concentrations of solutions using various methods and also describe how to prepare a solution of given concentration. This is a big, not big, but this comes up frequently in free response questions where students have to explain how a particular solution would be prepared. It's an easy point to get. Just make sure you understand this, the process. So this do now question: under which conditions of temperature and pressure would carbon dioxide dissolve best in water? So thinking back to our last lesson, carbon dioxide is a gas. What type of temperature would allow CO2 to dissolve the best, and what type of pressure situation? So it would have to be a cold temperature and a high pressure that would keep it contained. In this class, or in chemistry in general, there's different ways to express the concentration of a solution. The most common one you're going to see in here is the molarity, which you did in Regents chemistry. Molarity is equal to moles of solute per liter of solution. Mass or percentage by mass is another type. Mass of the solute divided by mass of solution times 100. Mole fraction we'll talk about more when we deal with gases, but since gases tend to be mixtures and homogeneous mixtures, mole fraction can be addressed here as well. I'm actually going to wait to address it till we get to gases in our next unit. Molality is one that you probably learned in chemistry, like your first year course, but it's not covered in AP Chem. So we'll spend some time talking about molarity here, which is moles of solute divided by liters. You must have those as your units. In most cases in this class, you'll be dealing in milliliters, so you have to convert it to liters. The unit for molarity, you can either use a capital M, or you can expand that and write moles per liter, or you could write moles times liters to the negative first. That might be how you see it on a reference sheet or in a problem. So first example here, quick way, calculate the concentration in units of molarity. So molarity equals moles over liters. We have 1 mole. We have 125 milliliters, which is 0.125 liters. And this would be an 8 molar solution, or 8 moles per liter. What volume of solution do I need in order to have 2 moles of sugar? So molarity equals moles over liters. We have a 10 molar solution, 2 moles over some liters, 10L equals 2. The volume would have to be 0.2 liters. The other way you could do this is by using factor labeling. 2 moles times, and this unit is moles per liter, we could flip it. Right, 10, this is 10 molar. If I flip it over, moles would cancel out, and I'd be left with the same thing. Get used to using molarity as a conversion factor. It comes up a lot. Third example, a 500 gram sample of potassium phosphate is dissolved in enough water to make 1.5 liters of solution. What is its molarity? You would be given the formula for potassium phosphate, because if you mess that formula up, you would mess up its gram formula mass and screw up the rest of your calculation. So that would be given to you. Its gram formula mass is 212.27 grams per mole. Okay, since we're looking for molarity, we need to have moles over liters. I have the liters part, but I don't have the moles part. I have grams. I can convert using the gram formula mass. So 500 grams times 1 mole over 212.27 grams. Well, that's 500.0. Make sure you write everything because sig figs. That comes out to 2.355 moles. So now we have 2.355 moles over 1.5 liters, and that would give us a 1.57 molar solution. This is a good one. Consider separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each solute in 250 milliliters of solution. Calculate the concentration of each in terms of molarity. So we have sodium hydroxide's gram formula mass is 39.998 grams per mole. Potassium chloride's is 74.55 grams per mole. So we have to first convert the 100 grams of sodium hydroxide into moles. That gives us, and then we can also just rope in the, what's it called? We can rope in the volume as well. We want the liters to be on the bottom, so we can just put 0.250 liters on the bottom. And that gives us 10.0 molar solution for the sodium hydroxide. And then we have 100 grams of potassium chloride, 74.55 grams per mole. Put that volume on the bottom, and that gives us a 5.37 molar solution of KCl. If you are asked a question like this in example 5, where you have to say how many grams of sodium chloride are needed to prepare 1.5 liters of 0.5 molar solution. So if I asked you to make me 1.5 liters of a 0.5 molar sodium chloride solution, you would have to go through these steps in order to do that. So when I make solutions for a lab and prep things ahead of time, I'm not just dumping salt into water and just calling it a day. The math has to be done first before you start to do your measuring and combining. So for this one, you want to ask, well, how much do I need? I need 1.5 liters. So that's what I'm given. So we'll work through this with factor labeling. How strong is it? What is the molarity? So that M could be expanded to moles per liter. So we'll do that to cancel out liters. So 0.500 moles per liter. Now the question is asking us how many grams. Well, I know how many I've converted now to moles. I can get to grams using the gram formula mass, which is 58.44 grams per mole, and get to my answer of 43.8 grams of sodium chloride. So I would weigh out on a balance 43.8 grams of sodium chloride, put it in a volumetric flask, a 1.5 liter volumetric flask, add some water and swirl it around, and then fill it up to 1.5 liter mark to make my solution. Another type of concentration problem you could be asked to do is a percentage problem. Anything you do that involves percentages is going to be part over whole times 100. So for a solution, the part is the solute, the whole is the entire solution. So here's a glucose solution, 5.5 grams. Now, when you divide, the division has to be over the whole solution mass. And the whole solution mass here is 83.7 grams. It's the solute plus the solvent. Water is not the solution. Water is just the solvent. And then we multiply it by 100, and that gives us 6.6%. Again, mole fraction we're going to skip over by now. This formula is on the reference sheet. So it's basically like a percentage, right? Part over whole, but you're not doing the multiplication by 100. You're leaving it as a decimal. Molality, again, is not in the curriculum, so bye. Okay, so if you were asked to explain how you'd prepare a solution, like in that earlier question with the sodium chloride, the calculation said, all right, I need 43.8 grams dissolved in my solution to make a total volume of 1.5 liters. So what you would do is you would use an electronic balance in a weighing dish. Oh, look, it's art. And you would measure out the mass of solute that you need. Then you'd use this piece of equipment. This is called a volumetric flask. A volumetric flask will have no markings on it except for one mark on the neck. That marking on the neck tells you the volume of solution that's capable of measuring. And I have these in all different sizes. I have them in 25 milliliters. I have them up to like a 2-liter size. So like 2,500, I have hundreds, 250s, 500s, 1 liters. So there's different volumes I can make. So I know if I want to make a 1.5 liter solution of that was like a 0.5 molar concentration, I need to measure out 43.8 grams of the salt. So the first thing I would do is I would put that solute into the solution. Into the empty flask. Then what I would do is I would add distilled water, enough distilled water that if I swirled it around, I could dissolve most, if not all, of that solute. Once all the solute has been dissolved, then I can continue to add more water until I get to that volume mark on the flask that tells me I have exactly 1.5 liters of solution. You don't want to fill it up to that mark and then shake it around, number one, because it's too hard to shake when the fluid is all the way up in the neck. And the other problem is that the volume might change once all of the solute has been integrated. So you want to fill up the bottom of the flask about halfway, swirl it around to dissolve it, and then continue to fill to dilute it to the volume that you need. If you had to dissolve a liquid solvent into a solute, like if you're making a solution of a certain type of alcohol, you would do a similar thing. You would calculate the volume needed. Let's say you're diluting an acid. Let's say you had a stock solution of 12 molar hydrochloric acid. That's what we buy it at. And you needed to make 500 milliliters of a 3 molar solution. Well, you would use M1V1 equals M2V2 to do your dilution problem, and you would calculate how much of that 12 molar acid you would need in order to make your solution. Now, with liquid solution preps, liquid solutes and solvents, you want to put a little bit of water in the bottom of the flask first. Then you'll use a pipette or some sort of, you've already measured out how much of the concentrated solute you need. So like that would be the full strength acid, because you always want to add acid to the water. Once you've diluted it somewhat by adding the concentrate to some of the water, then you can continue to add water to the calibration mark. Okay, so for this calculation, if you are asked to find the concentration of particular ions in a solution, you have to look at the formula of the solute as well as the concentration of the solution. So if I have a 0.25 molar calcium chloride solution, when calcium chloride dissociates, I get 1 unit of calcium and 2 units of chloride. So that means the concentration of the calcium ions is one of those ions from the formula times the concentration of the solution, which gives me 0.25. And then the concentration of the chloride ions, since I have 2 of them in my formula, the concentration of chloride ions is actually twice as much as the concentration of calcium ions. Another thing to remind you of, when you see brackets around a symbol, that means concentration or molarity. So number 7 here, which of the following solutions contains the greatest number of ions? So what we can do here is we can figure out how many ions are present in each of these choices. So for choice A, we have 0.4 liters times 0.1 moles per liter times, well, how many total ions are in my formula? 2 moles of ions are present in 1 mole of the compound. So that comes out to 0.08 moles of ions present. For choice B, I have 0.3 liters times 0.1 moles of compound per liter times 3 moles of ions per unit of compound, because I have the 1, 2, 3. And that comes out to 0.09 moles of ions total. Choice C, 0.2 liters times 0.1 mole per liter times, well, how many moles of ions do I have in this compound? 4. And that is 0.08 moles of ions. And for D, I have 0.8 liters times 0.1 moles per liter. Now I have sucrose here. Sucrose is sugar. Sugar is covalent. Covalent substances do not dissociate in water. So I have 1 mole of particles per mole of compound, because these C's, H's, and O's don't separate from one another. They stay intact. So this is 0.08 moles. We have no ions here. So the one that has the greatest concentration of particles overall would be choice B. So notice the solution with the greatest number of ions isn't necessarily the one where you have the greatest volume or that has the most number of ions in the particle. So the total volume of solution comes into play, the total molarity comes into play, and then the molarity of each of the ions comes into play as well. Dilution, this formula, I don't think it's on the reference sheet, but dilution is something that comes up a lot. So the dilution is the process of adding water to a concentrated or stock solution to achieve a desired molarity for a particular solution. when you dilute a solution with water, it doesn't change the number of moles of solute that are present. It just changes the concentration, which is moles of solute per unit of volume. So the moles of solute present prior to diluting is going to be equal to moles of solute after the diluting. So that's where this comes into play. The initial molarity, so that's the concentrated one, times the volume of concentrated one equals the new molarity, the diluted one, times the volume of the diluted solution. So in terms of units, let's see why this works. Molarity is moles per liter, times volume, which is liters. That gives me moles for the left side. And on the right side, the new molarity times the new volume, which is in liters. Well, that gives me moles as well. It's going to give me the same number. So number of moles prior equals number of moles post. So here's this example, a 0.5 molar solution of sodium chloride in an open beaker. So think about what's happening here. Sometimes I like to make these little sketches to help me out here. So I have a 0.5 molar sodium chloride solution. It's in an open beaker. It says on a lab bench. Which of the following would decrease the concentration of the salt solution? So I want the molarity to go down. So what could I do to this solution to decrease the molarity? Could I add water to the solution to decrease the concentration? Could I pour some solution down the drain? Could I add more sodium chloride? Let the solution sit out in the open air for a couple days, or at least 2 would decrease the concentration of the solution. Well, what I could do to decrease this concentration would be add water. When I add water to the solution, I'm diluting it, so the number of moles of sodium chloride will stay the same, but since the volume went up, the volume of the solution went up, the molarity would go down, right? Because if I have moles over liters, 0.5 moles over liters, and I increase the volume here, this higher number, when I redo the division, is going to make my answer smaller. If I poured some solution down the drain, that's not going to change the concentration, because assuming this is a homogeneous mixture, if I start pouring some of it out, my volume of solution will change, but the number of moles that went down the drain would be consistent. Add more sodium chloride, well, that would increase the concentration. Let the solution sit out in the open air for a couple days. Well, what would happen if I let this sit out in the open air? The water would slowly start to evaporate, so this volume would drop. If the volume gets lower, the concentration would go higher. And then, choice E would be wrong then. Last example here, here's a dilution problem. What's the minimum volume of a 2 molar sodium hydroxide solution needed to make 150 milliliters of a 0.8 molar sodium hydroxide solution? So since we're changing the concentration of our solution, we can do M1V1 equals M2V2. So my initial solution has a concentration of 2.00. The volume I need is my unknown. I want to make a 0.8 molar solution, and I want to make 150 milliliters of it. You could convert this to liters if you want, but and then your answer for V1 would be in liters, or you could just leave this as milliliters, and then your answer over in V1 would be in milliliters as well. And this comes out to 60 milliliters. If you had converted this to liters and made this 0.15, you would end up with 0.06 for liters for the volume. So we've looked at what molarity is, how to solve problems involving molarity using a set of different conversions, how to deal with mass percent problems, how to prepare a solution, and how to dilute as well.